Am I audible?
Yes, sir.
Okay. So is the volume okay, or should I speak louder?
Could you please volume?
Sorry?
Yes, sir. Can you be louder?
Okay. Is this better now, or?
Yes, sir.
Okay, we'll start in 2 minutes. Just 2 minutes. Okay, so the plan for today is the SVM is long overdue. So the soft margin SVM implementation will work through that, and the other part would be K-means clustering for week 11. Nitin unfortunately is not able to take the session today. So week 10 and yeah, week 10 boosting and bagging, there will be one session tomorrow from 4 to 6 p.m. So bagging and boosting will be discussed during that session tomorrow. Today it will be SVM and clustering. I hope that plan is okay. Is that fine with all of you?
Sir, is MLT also having a project or something?
Sorry?
Is MLT also having a project?
No, no. There is only one project for the ML courses put together. That's all.
I actually see in my calendar that meet is scheduled for tomorrow MLT project discussion.
No. That is only for those who have registered for the project. You are doing MLT alone, right? Or you are doing both?
No,
MLT.
I'm doing both.
You're doing both, right? Okay. So.
But it says MLT project discussion, not MLP.
Oh no, no, sir. I think someone has made a mistake.
Yeah.
I'll ask them to correct it. Okay, so there is no project for MLT as such. There is only the theory part and the programming part. Okay, any other questions before we move ahead?
I have some doubts regarding week 10 and week 11.
Okay, week 10 will be discussed tomorrow. Week 11 while we do K-means, we'll go over that.
Should I ask it after you have explained the soft margin?
Yeah. So once we start doing K-means and we reach a reasonable stage, right, we'll discuss.
Have K-means in your schedule. Okay, sir.
Okay, so I hope you all remember what is soft margin SVM. Okay, so we have some data set like this, and this is the objective. We have one term for maximizing the margin and another term for the hinge loss. That hinge loss is governed by the trade-off between these two is governed by this parameter C, and we have to compute the gradients and then do gradient descent. Right. So theoretically, the plan is straightforward. So we have to now do this, code this up. So you can, if you're interested, you can open a collab and you can code in parallel. Okay, so I'll just get started. So we'll import NumPy and matplotlib. Okay, so the first thing I'll do is, if you remember several weeks back, we had one default, a random number generator. So I'll just go ahead and get hold of a random number generator. So seed value is important because you want your experiments to be reproducible. So this is for read. Okay, so we do that. And the other thing is I want my graphs to look slightly bigger. So I'll just go ahead and make sure that my figure size is 8 cross 8. Okay, so this is the basic setup that I'm going to do. Initialize. Okay, collab is initialized. So now, once these things are out of our way, we will play around with some custom data, right? Some toy data set. So again, if you recall, we did this using multivariate normal with some mean and some variance. So mean, I'll just take this to be, let's say, -1 comma -3, right? So something like that. That will be my mean for the first set of data points, class 1 or class 0. The other mean will be, let's say, 2 comma 3, right? So these are the two means, and my covariance matrix, I'll just choose it to be identity. Okay, so we are going to sample, say, 25 data points from each class, so that will be n equal to 25. So now sample 25 points with mean mu1 and variance sigma, covariance matrix sigma, and number of points is equal to n, right? So this will be my data points that belong to class 1, and this will be the set of data points that belong to class 2. Okay, so just quickly plot x1 and x2 just to make sure that in fact there's a simpler way to plot. Okay, so just to know if people are there in the call, how do I club these two together and turn it into a single feature matrix? What command should I use?
Column stack.
Okay, column stack is one. Anything else?
Excuse me, sir.
Yeah.
So we can use concatenate also, right?
Okay, we'll use concatenate now. Concatenate. I am concatenating x1 and x2. Along what axis should I concatenate?
I think should be across columns, is it?
Okay, axis. Yes, axis should be 0 or 1. So 0 or 1.
First.
You are saying 1. Is it?
Should be 1, yeah. Yeah.
Okay, okay. Okay, let's see. X1 is of what shape? What would be the shape of this array? X1, x underscore 1?
25 comma 2.
Okay, this would be 25 comma 2. Okay, so this x2 is also 25 comma 2.
Yeah.
Now, if I run x dot shape, what do you think will be the shape of x?
25 comma 4.
Okay, is that the way we want to concatenate them? Okay, just run this. So 25 comma 4. So this is not the way we want to club them, right? So we want all data points to be of 2 dimensions, right? So we need to do axis equal to 0, right? Along the rows, we have to concatenate. Is that point clear?
Yes, sir.
Okay, so this is along the rows. So this is what we have done. Now, so y1 will be what? What should be the labels for class 1 in SVM?
-1.
One and
List of -1s.
yeah, it will be a list of ones and minus ones, right? So
Not ones.
this is
Beautiful.
these are all ones and this is all minus ones. I'll do the same thing. I'll concatenate y1 and y2. Here I don't need to specify the axis because they are all vectors, right? So single dimensional numpy arrays. So there is only way to concatenate them is along one. There's only one axis basically, right? So that is the advantage here. So let's now verify that we have the right kind of objects. If we print the shape, we have 50 data points belonging to R2 and their labels are 1 or -1. Okay, so this is the data set available to us.
Sir,
Yeah,
I did not understand the fourth and fifth line.
this line, right?
Sir,
Okay, so this is, I mean, not very important from the point of MLT, MLT as such. See, what we are doing is there is a Gaussian distribution, a multivariate Gaussian distribution. Okay, so you are just sampling from the distribution. You are just generating a bunch of points which you can use to train your classifier. Okay, so if I plot them, it will become clearer. So I'm going to plot these set of points. So all x coordinates, all y coordinates, and you can actually give them this color this way, right? So plot won't work. We have to do a scatter plot. So if we run a scatter plot, let me. Okay, so see this. All that I'm saying is that generate 25 data points centered at -1, -3. Okay, with some variance, covariance. That is all I'm saying in those two lines.
and sigma.
Sigma is just, so sigma is what is called a covariance matrix. So for example, if I let's say I generate 1000 points, if you look at the points, you can see that they are all kind of, the distribution is circular, right? So my sigma controls two things. So one, it controls the shape of the kind of distribution I obtain. The second thing it controls is the spread. So if I, for example, reduce the sigma by, if I make it very small, you will see that the points are much more closer to each other, right? So they are the variance in some sense. You can treat sigma as the variance, right? It's not very accurate, but you can think about it as the variance in the x and y directions. So the smaller the sigma, smaller the variance. So that is what it controls, sigma. Okay, so let's go back to 25 points. All right, so this is the data set, right? So we now have the data set. Any questions so far? Anyone? Okay, so once we have the data set, the next step is, I'll not write the class first. We'll write the class later. First, we'll go ahead and compute the loss function, right? So I'm going to write the template, the signature for the loss. So what parameters do you think the loss function should take?
The predicted values and the actual values.
Okay, predicted values. Okay, but the objective function requires the weight, right? So weight bias. So if you study this equation, what all do you think I need to compute this loss?
The weights, bias, Data points.
Right. So weight, bias, data point, and also I'll also probably need the value of C, right? So I'm going to just throw the whole thing inside. First, I'll throw the data set inside. X comma Y I need. I also need W comma B, the parameters of the model. I also need the hyperparameter, which is the C value. Okay, so I need all these things if I have to compute the loss. So let's compute this margin term first because it's easy. So how I'll just call this the margin term. So what should be the expression for that? Norm W square by 2. In NumPy, how do I do that?
W transpose W.
Okay, W transpose W over 2, right? So that is the margin. Now we come to the hinge component.
Can you do np dot square for W
NP dot.
square?
That is also okay, but you can't just do NP dot square. You have to do NP dot. I mean, I don't know if NP dot square is there, but you can do something like this. You can square W and then you can sum it across all the. This will also work.
Or we can also use dot product for.
Yeah, or you can use NP dot of W comma W. Yeah, that also works. So the reason I went for probably the first option is this norm W square is W transpose W. So the thing that probably you can look for when you are giving the OPP or in general is when you are translating from mathematical expression to NumPy, go for the most direct translation, right? So this is also all these three are correct, but this is in some sense like a replica of the math formula, right? So the only thing I've done here is that at I have added and this dot T I have added for the transpose and the matrix product. Okay, so this, if you can keep this translation in mind, it will be easier. This is also correct, and these are not wrong, but you go for that which is closest to the math expression. Okay, so how do you compute the hinge loss in NumPy? Okay, let's break it down into two parts. How do you compute this? You need to compute this. Yi into W transpose Xi plus B.
Excuse me, sir.
Yeah.
May I add something?
Yeah.
Yeah. So since we have the data points already with us, what we can do is we can do X at W so that at once it computes for the entire data set.
Okay.
And then add the bias term after that.
Okay, we'll do that, right? So what we'll do is we'll call this a linear combination of X, Y, what all do we need? X, Y, WB, right? So we'll call it X, Y, WB. So as you say, we'll do X at W plus B. So this will give us the W transpose X plus B for all the data points. Now, how do I get this part? Ya into W transpose X plus B, what should I do?
I think it's like a hard mod.
Okay, correct. Okay, so I just need to multiply this by W, right?
Yeah. Start by, yeah.
Okay, so did everyone get this? Others, are you all like, are you all following, or is there something that is not clear? Did everyone get this? A show of hands would also be enough.
So like you multiply by y, shouldn't we use at the rate instead?
Okay, so see, okay, let's take this in two steps. So what is the dimension of X? Can you tell me what the dimension of X will be? In our problem, we have 25 data points and two-dimensional features. So what do you think will be the shape of X
50, comma 2.
It will be 50 comma 2, right? So that is correct. What will be the shape of y?
50.
This will be just 50 vector, right? What will be the shape of w? We have not yet defined it, but intuitively, what do you think it should be?
2.
It will be 2, right? So now, what will be the shape of x transpose w plus p?
50.
This will be just 50, right? So extra xw, sorry, not x transpose w, xw plus b is a vector of size 50, y is a vector of size 50, right? So this is xw plus b is the linear combination for all the 50 data points, and y is the label for those 50 data points. So what you need is element wise product, right? So data point wise product. So you so that's the reason why you just multiply them element wise. That's why you use the star. Okay, so you want the first element of xw plus b to be multiplied with the first element of y. Likewise, you want that to happen for all the 50 elements of the linear combination.
Excuse me, sir.
Yeah.
Just to clarify, the order of that, I mean, y into x at w plus b is the same as x at w plus b, and then at into y is the same thing, right?
Sorry, what is the first one you mentioned?
That x at w plus b, and then we have the star y is the same thing as if we kind of if we reverse the order, it will still be the same, right?
Oh, okay.
Just wanted to confirm that.
Yeah. You meant like y into,
Since
right?
it's just the product element wise multiplication, so should not be like affecting. I mean, the order should not matter. Yeah.
Right. Yeah. This is the both are equivalent.
Okay. Yeah. Oh, sure. Thank you.
Okay, so I'm assuming others got this, and I'm proceeding. So if you have any question, please stop me. Otherwise, I'll assume that you all know. Okay. So yeah, that is the linear combination. So we have got this part of the product. Now we'll come to the hinge loss. So what I'm going to do is I'm going to make use of the linear combination x, y, w, b. Okay, so now how do I write this part of the hinge
NP
loss?
dot where that term is less than 0, make keep it that, and else do it 0.
Right, agreed. But before that, if we have computed only this part, right? How if you want the whole thing, we just need to do 1 minus this, right? So
Yeah.
so we are doing 1 minus this. So what you said is correct, because we could do np dot var, but it turns out, I mean, I also did np dot var first, but it turns out there's another way you can do this. So this function is that in NumPy called np dot maximum. So I'll just demonstrate this. So assume that you have something like this. You have a vector like np dot array of 1 minus 1 2 3 minus 4 5, right? And I do np dot maximum of 0 comma vector. Okay, and if I run this, it will do something interesting, right? So wherever the elements of the vector are negative, it will replace them with zeros. And wherever the vector has positive elements, it will retain the value of that element, right? Which is what we want here, right? We want wherever this term is negative, we want to make it 0, and wherever it's positive, we want to retain that value itself. Okay, so this max of 0 comma, that term is obtained this way.
So we can also write np dot max, right?
I am not sure. So np dot max, what does it do? Np dot max.
I think max will be for the scalar values.
Scalar values, is it? I don't know. Let's try np dot max. See, np dot max of vec alone will give you the maximum of this vector. But what happens if we do? Okay, so this is a different function, right? Only integer scalar arrays can be converted to a scalar index. So this just returns the max of that particular vector. I'll just let's look at the help function. What does np.max do? So it returns the maximum and minimum value. Okay, maximum value of an array along the given axis. Okay, so that is what it does. Now, what about np.maximum? Oh, it keeps going on and on. How do we look at only that part?
Try doing just the question mark of np.maximum.
This way, right?
Yeah.
Oh, nice. Okay. np.maximum. So it does element-wise maximum of array elements. So compare two arrays and returns a new array containing the element-wise maximum. Okay, so this will also work. Let's say if we have something like vec1 and vec2 is say 5, 0, 2. Then if you do np.max of vec1 comma vec2, then it will give us the maximum element wise across these two arrays. Okay, here what we have done is instead of having another vector, we have just used a scalar 0, but that broadcasts itself across the length of the array. So we are safe there. Okay, so I hope np.maximum it's clear what's happening. Okay, so this is the hinge loss. Is this correct? Is this the correct expression for the hinge loss?
Now we have to sum it up.
Correct, right? So we have to sum it up. This is for all n data points. Now we have to sum this thing up. Right, so sum this up and then multiply by the hyperparameter C. So that is our hinge plus margin. So I'm just going to return this, right? So that is the objective. I hope this is clear. Okay, so now comes the gradient. So the gradients again we see that we have to plug in all these values x, y, w, b, c. Okay, so all the values are there. So first we'll look at the gradient of the loss with respect to the weights. Okay, how do we get the gradient of the loss with respect to the weights? This part is easy, right? So it's just W transpose W over 2. The gradient is just W. So I'm just going to add that. Now, okay, so now can you tell me how to do this part? Anyone, any ideas?
The second part of the objective.
Yeah, so the second part of the objective. I mean, the
argmax, we can use argmax.
Okay, yeah.
And sum, np.sum.
Okay, so what I'll do is, first I'll get hold of this again. I'll get hold of the linear combination. I'll break it into that. So let me.
We can get the index of all those data points.
Yeah. So very first step, yeah, before we get the index, you are right. So, but before we get the index, let me get hold of the linear combination of all the data points. That is XYWB. Okay, and 1 minus that is what I am looking for. So 1 minus the linear combination. Okay, so this is now okay. So where are these points greater than 0? Okay, so what I'm going to do is I'm going to look at where all those indices where these points are greater than 0, set them to 1. Rest of them are going to remain 0.
Sir, we
Yes.
can get directly the index. Then we can do whatever we want with that. No?
Okay, so that is also a good point. So how do you get the index?
For that, you just like whatever you have written, that is enough, and just remove that 1 comma 0, whatever conditions you are giving, uh, and at the end just add a 0, because when we are using np.where without any like what to do when these conditions are met, then it returns a tuple. So in that tuple, the first part is all the index, and the next part I don't know what it is, but the first part is index. So we have to do.
Okay. Okay, so I'll do it in a particular way, and then we'll also look at the method you're suggesting. Okay. Okay, so what we need is so this is going to be a set of points where this is greater than 0. Okay, so just give me 1 second. Okay, so I'm going to do the following. Let me know if this makes sense. I'm going to multiply this by x and y. Does this make sense?
So it retains the value of x where that np.where condition is satisfied.
Right. So let's just take one step back.
Yes, sir. This is also. I think it is correct.
Right. So let's just quickly take one step back and look at the sizes that we are dealing with. So what will be the size of this? This will be of size, say 50 data points, right? So this will be of size 50. It's a vector of size 50. Now this np.where, wherever this linear combination 1 minus this combination greater than 0 business, basically all those points which have violated the margin, right? So that is what we are looking at. We are looking at the points which have violated the margin, and wherever the margin is violated, that at that index we'll have a 1, at all the other indices we'll have 0. So this again will be of size 50, right? So this will be a vector of size 50. X will be a vector of size 50 comma 2, and y will be again of size 50. Okay, so when I'm multiplying these three arrays, broadcasting will be a problem, right? So I can't multiply this with these two. So what I am going to do is I'm going to multiply this with y. See, these two are 50 and these two are 50. So I have no problem multiplying these two values, right? And then, but here, just to make the shape all right, I'm going to just reshape it to -1, 1. So when I do that, what happens is this becomes 50 cross 1, the first product, and the x is anyway 50 cross 2. So now I can multiply these two. So the result will be what? The result will be a 50 cross 2 array where several rows will be 0, and only those rows in which the data points have violated the margin, those rows alone matter.
So I have one doubt.
Yeah.
Can you explain this broadcast rule again? It means the first element of the tuple should match. Then only we can broadcast.
So the broadcasting rule works from back. So there are it's like a bunch of rules. I am also not very clear, but the one important rule is that when you look at the two arrays from the end, the last dimensions should match. Either that should happen, or one of the last dimensions should be 1. So for example, let me take one. Let me take this case where things are explicit. So let's say A is one array. So let's write it this way: 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is some 4 cross 3 array, and what I want to do is, let's say the first and last examples are violating the margin. So I'll have something like this. I'll have a 1 here, 0 here, 0 here, 1 here. So what I want to do is I want to multiply B with A, but I want to multiply B such that it multiplies the columns of, it's like I turn B vertically and then multiply it across the columns of A. That is what I intend to do, right? That is the effect that I want. So,
right.
So let's see if simple A into B will work. So it will give you a broadcast error because the shapes are 4 cross 3 and 4. Okay, so the basic broadcasting rule says that the last dimension should either match. In this case, they don't match because here the last dimension is a 3, here it's a 4. They don't match. So either you make them match or make one of them 1. So here I can't make this 1. So I'll make the B part 1. So what I'll do is I'll reshape this to -1, 1, which is 4, 1, right? So when I do this, now you see what's happening. I am able to do this multiplication, and the first and last rows are retained. All the others become 0.
Okay, sir. Thank you. Thank you for that.
Okay, so this is what we are doing here. We are looking at all those points which have violated the margin, make them 1, make the others 0, multiply them with y, and reshape them so that the broadcasting rules are satisfied. Now multiply that with the data matrix 6. Right? This is what we have here. And since we are summing over the n examples, we have to. This is not enough. You have to do np.sum across the whole thing, and that will be the hinge loss, the contribution of the hinge loss to the gradient. Okay, so this C into this will be the whole thing. Now I need W minus the whole thing, right? So this will be gradient of the loss with respect to W. Now, is this clear to everyone? There were like several steps here.
Excuse me, sir. May I ask a question?
Yeah.
So this was regarding that reshaping that we've done, -1, 1 in that example.
Yeah.
In the line number, the fifth line actually in the that the other example that you showed. Yeah, here.
Right.
So is this in this particular case the same as when we take the transpose of it of B? I think it should be the same. I think I don't know,
but yeah. So see, the problem is if we you're saying why can't we just so
Yes,
if we
sir.
do this, the problem will persist. The reason is B is just a single dimensional array, right? So B and B transpose are going to be the same. So if you look at B is just a single dimensional array. So if I do B and B transpose, it will still be a 1D array. So B dot ending, if you look at it, it is 1.
Right, sir.
Right. So I am forced to do this reshape so that it becomes a 2-dimensional array with the second dimension being whatever 4, second dimension being 1.
Okay, all right. So I was thinking that the other, when it is not explicit, is already 1. I mean, I was under that impression that if it is not 1, it is 1-dimensional. So it is already, I mean, assumed to be 1. But
Okay.
it seems that is not the case.
Yeah. So in our this is we have been a bit slack in the assignments, but whenever we say weight vector, it should always be a vector. I mean, it should always be a single dimensional array in number. That is the convention that we should follow. Okay, so any other questions regarding this? Whatever we did here, computing the gradient. Okay, so I am assuming there are no other questions in proceeding. Now the gradient with respect to B is very simple. We just need to copy this. Okay, copy this part, remove the W part, retain the minus sign, and delete the X from it. Right. So here the nice thing is we don't need to reshape. We need to. Why is that not required anymore? So everyone see why that is. The reshaping is not required anymore.
Because we're not multiplying with X.
Right. Yeah. So you're not multiplying this with the matrix X. So this is anyway a vector. This is also a vector. So you end up with this part, right? So we have the gradients. Now all that remains to do is, of course, return the gradients. Okay, the final part is going to be quite easy. We just need to fit our model to this data set. So let's choose some random set of weights. So I hope default.rng is that. Let me just check. It should be RNG. So I am drawing from a normal distribution. So I need to specify the size, right? So let's say I draw a 2-dimensional vector. This is how we do it, right? So I am drawing a 2-dimensional vector. So, but in general, what will be the shape if I don't know the number of dimensions a priori? How do I get it from the parameters? What should be the size of the weight vector in SVMs?
X dot shape of 2. 1, sorry.
Yeah, X dot shape of 1. Right. So get hold of a random weight vector of shape X dot shape of 1. B is say in this RNG dot normal without anything, just returns a single number, I guess. So we'll stick to that. So once you have the W and B values.
So in line 12.
There is a typo in line 12.
Oh, okay. What?
Grad
Very
underscore
good.
B. Yeah.
Okay. Yeah. Thanks. You are so paying attention. That is good. Okay. So for set number of epochs, let me specify. So what other hyperparameters? So C is the model's hyperparameter. The usual hyperparameters for gradient descent, what are they?
Epochs, learning rate.
Learning rate.
Okay, epochs and learning rate. Right? So let me give default values to this. Epochs is 1 and say 100 epochs. Sorry, epochs is 100, learning rate is 0.1. Right? So I iterate through each epoch, and the first thing I do is compute the gradients by calling the gradients function. Okay, and then W equal to the update rule, right? W minus learning rate times the gradient. So W minus grad W LR into this, and B equal to B minus learning rate into gradient of B. Okay, so I also compute the loss at every epoch. So that is XYWBC, right? So pass the data, pass the parameters, pass the hyperparameter. And I want to keep track of the error so that I can plot it later on. So I initialize a matrix and append my loss to that matrix. Okay, and finally, once I'm done with the training, I return my parameters, model parameters, and the loss mat and the list of losses. Okay, is that clear? The fit function, is it clear? Any questions? Okay, so if there are no questions, we will see how well the fit is. So I'm going to run this for 100 epochs for C equal to 1, let's say. In learning rate, let's not meddle with it. So fit the function to the data set that we have created. We also specify the learning rate just to be safe. It returns weights, biases, and the losses, right? So what we can now do is we can now plot the losses. Plt.plot. So on the x-axis I have the epochs, on the y-axis I have the losses, right? So let's run this and see. We might get some errors. So fit is not defined. It's because we haven't run this. So fit got multiple values for argument C. That is correct. Okay, so that was fast. So let's go ahead and visualize if whatever we have done is correct. I'm going to get hold of these data points again. So is everyone there with me? Are you lost, or is it all okay?
I think it's okay for me at least.
It's
Okay. Okay, if you're lost, please tell me. See, because I don't know if some of you are silent because you don't understand, or because I mean, there are two ways to be silent. Okay, I hope you are all following the whole thing. Okay, so what I'm going to do is it's the same data, but we are going to plot the decision boundary on top of this. So we have the W and B value, right? So W and B. So the decision boundary is going to be W transpose X plus B equal to 0. So that is like W0 into X1 plus w1 into x2 plus b equal to 0. Now, if I want to do this in NumPy, what I'll do is I will write it in the form y equal to mx plus c, right? So I'll do x2 equal to minus w0 into x1 plus b divided by w1, right? So I just write it in this form. Only then I can plot it. So let me take a set of points on the x-axis, let's say from -5 to 5, equally spaced points, 100 points, and my decision boundary will now be this x-axis, set of points on the x-axis, and this thing, right? So color can be black, right? So okay, what is, it's not x1, this is x, right? That is the error. Okay, so this is the decision boundary that we are getting, and yeah.
Can you explain this part again, sir?
So the decision boundary.
Decision boundary, yes, sir.
Yeah, see, the decision boundary basically is what w. Let me just write the equation here. So the equation of the decision boundary is w transpose x plus b equal to 0, and in our case it is, I mean, using zero, what is that called? Zero indexing. It is, or let's use the normal indexing itself. So w1 x1 plus w2 x2 plus p equal to 0. Now what I'm doing is I'm writing it in the form x2 equal to mx1 plus c, right? So this becomes w minus w1 x1 minus b, the whole thing divided by b. Sorry, not b, w1. Oh, sorry, w2. Okay, sorry, w2. So that is what I that's what I've written here.
Okay, sir.
Okay, so any other questions?
So instead of using this, like we can just write x column 1, x column 2 instead of writing this equation.
Sorry, can you come again? X column.
Like we need x1 and x2 here. So it's these are like features like we have in X matrix. So we can just write x0 and x1.
Yeah, that is correct. That is what we have done here, right? So we have done, so for plotting the data points, where is the, so yeah, for plotting the data points, we have done that, right? Scatter plot. So x0 and x1, that will give me these blue and yellow points, but for the decision boundary, I need to plot a line, right? Line is of the form mx plus c, and that is the reason we are doing this.
What does like x2 indicate here? Like x2 and x1, like here.
x2 and x1 are the features, right? So the, sorry, not features. Yeah, features. x1 is the x-axis in this case, x2 is the y-axis.
Then why can't we just use directly like x1, x0? Directly, like we can write first row and second.
Right, but how will you plot the line? You need to plot the line, right? See, I agree that if you use x1 and x2, you will get these points, right? But what about this line? I need to, how do you plot a line? You need this mx plus c form, right? Unless,
so you need like more features.
No, not features, right? See, features are only two. I have only two features. For the decision boundary, you don't need the features, right? You just need the. Do you get the point? I mean, you don't need the data points for plotting the decision boundary. You just need some relationship between the feature 1 and feature 2 as variables. So, see here, x1 and x2 are not. They don't represent any data point. They represent some arbitrary point in the plane or on the line rather. see here, x1 comma x2 is a point on the decision boundary, right? So what is x1? X1 is some arbitrary value, right? Some real number. And in our case, what I've done is for in NumPy or Matplotlib, if you want to plot a line, you need some range of values. So that's why I've considered x to be in the range -5 to 5. This x, if it is not clear, is actually this x1. Is it
We can
clear?
rename it to maybe D1 decision.
Yeah, okay, yeah, that may be clearer. So let me just call it D1, D2. And what I'm doing is, this is the decision boundary. D1 comma D2 are points on the decision boundary, and I am plotting D1 and the corresponding D2 value. Okay, so that is, I think, yeah, that should be clearer now. This is D1, D2, right? And this D1, D2. So this is what we are doing. Yeah, that was a good change of notation. So
basically, for all the D1, you are calculating the D2s.
yeah, for all the D1, for all the D2s, we are calculating. Right. So now, what we'll do is we'll also plot the bounding planes. Right. We need to plot the two bounding planes, which is W transpose X plus B equal to 1 and -1. Right. So that is simply like adding 1 and -1 here. Right. So okay. What is this? Should be the variable here, marker or okay, this should come before apparently. But let's move this out.
But if we are giving named parameter, then order does not matter.
Order, yeah, you're right. Order does not matter, but apparently the marker name is wrong. Maybe it's marker style or. Okay, so this is the image that we get for whatever we have done so far.
So I had a question regarding SVM in general.
Yeah, yeah.
Does SVM minimize the number of support vectors too?
Yes, it minimizes the. I don't know if it minimizes. See,
Actually,
yeah.
So there was a question in the quiz in which we had to make a decision boundary. So the answer was like a slanting decision boundary like this. But I thought that SVM also minimizes the number of support vectors, and those were getting minimized in like a horizontal support boundary.
Okay,
decision boundary.
All right. Okay. See, it doesn't minimize the support vectors for the reason that the support vector, it doesn't begin with SVM doesn't begin with the concept of support vector, right? So the only thing it does is it tries to solve the optimization problem as presented here, and whatever lies within the margin becomes support vectors, right? So there is, yeah.
Sir, but one criteria by which we judge SVM models is by the number of support vectors they have. If they have more number of support vectors, we say that the model is not that good, and if they are like really less, we say the model is good.
Agreed. Yeah. So I agree with that point, but that is a question of interpretation, right? So yes, whatever SVM you obtain is a bad model, but that's the only SVM you would have obtained, right? But even if you train again on that particular set, you would end up obtaining that many support vectors, right? So it's with SVMs, this is all you can do, but you don't explicitly set out to minimize the number of support vectors, right? So that is not a part of the objective.
Okay.
Okay, so that is not there in that.
Sir, here if we see the model, it is slightly towards the blue points instead of the yellow points. So can we rectify that by the number of epochs?
Yeah, so yeah, I want to share a few other images. Let me. This is actually interesting. The whole, we haven't analyzed this properly at all. So I'll just show you some experiments that I have done offline, and for different values of C. Okay, so I'll share my. For this, I need to share my desktop. Are you able to see the desktop screen?
Yes. Yes.
Yes.
Okay, see what's happening is whatever code we have written, and I have just run this for different values of C. Okay, so let me first show this for the value of C equal to 0.0001, right? 10 power minus 4. Is this image visible to all of you?
No, sir.
Yes.
You are able to see a graph, right?
No, sir.
Right.
The thumbnails are visible to us, not the image.
The thumbnails are visible.
Like for every image.
Oh, okay.
Previews of every image.
Oh, right. So I am. Okay, how do I show you? I think I need to share that particular screen then. I need to show you the image viewer. Okay, now is it visible?
Yeah.
Yeah.
If I change it, is it visible?
Yes.
Yeah.
Okay. See, what is happening is, this is the loss for this particular SVM. It's epoch 1, and the value of C is 10 power minus 4. This thing here, it gives you the percentage of the contribution of the hinge loss to the total loss. Okay, remember that the hinge loss, there are two parts to the loss, right? One is for the margin, one is for the hinge loss. And the hinge loss, what contribution does it have compared to the total loss? So 6% of the total loss is the hinge loss. Okay, so now this is in epoch 1, at the end of epoch 1. So what do you think will happen if I go to epoch 2?
Green would rotate and so
Should improve.
Margin should come closer.
What should come closer?
The margin should come closer, sir.
Okay, see, it has something to do with the margin, but should the margin come closer or should it go wider? Remember that this value of C is very small. So
it will try to maximize the distance. So it will go wider, sir, I think.
Okay, so that is what happens. It goes wider, right? Because the first term, remember, is norm W square by 2. Okay, I'm minimizing the loss. If norm W square by 2 goes down, the margin is going to increase, right? We are maximizing the margin. So the first term of the loss is equivalent to maximizing the margin. So for a very small C value, very small C value, what is going to happen is that my model is essentially free to maximize the margin as much as it wants, right? So also notice that the hinge loss, the percentage, it keeps on increasing, right? So if I keep running this, there is a point reached when the hinge loss contributes nearly 95-96% of the loss, and because of that, the decision boundary is changing, if you notice. Right, so I keep moving, and then at some point what happens is I kind of saturate.
So when the value of the percentage of the hinge loss becomes too high, it tries to minimize the hinge loss from the instead of maximizing the weights.
Yeah, instead of so the focus shifts from the margin to the hinge loss. So that is why we were even able to change the boundary, right? So otherwise, see, the margin the margin kept on increasing. At some point of time, the contribution of the hinge loss became sufficient. Say at this point, if you see, we start moving from maximizing the margin to fixing the hinge loss. So that is why the boundary significantly changes over the next few epochs. But at some point, what happens is this thing also saturates and nothing else can be done at this stage. Okay, so the moral of the story here is that when C is very small, the model doesn't worry too much about the hinge loss, and it's going to maximize the margin. Now, if you actually zoom out from the image, you will notice that the margin is like way out on either side. Okay, so that is one image. I'll show you what happens when are you able to see the case for C equal to 0.01? Is this visible now?
Yes.
Okay, so see here something interesting will happen. At the end of epoch 1, the hinge loss is already having a big contribution. Okay, so my boundary is drastically changing so as to minimize that, right? So in epoch 2, hinge loss comes down. In epoch 3, it comes down further, keeps going down, right? But slowly it's kind of stabilizing. Right, so I want to stop the image at this stage and ask you how many data points are actually contributing to the hinge loss. If you study this image, how many data points are contributing to the hinge loss?
From the red and 3 from the green.
How many from the red?
6.
Okay, 6, 1, 2. So we have 1, 2, 3, 4, 5, 6 data points from the red, and 3 from the green are contributing to the hinge loss. I hope so. This is very important for all of us to know. Okay, so these are the data points which are responsible for the hinge loss. Okay, now what will be the classification accuracy of this model?
100%.
100%, right? So that has nothing to do with the hinge loss. Okay, so the model is predicting 100% correctly, but still we have some hinge loss. So I'll keep going forward. Now notice that the hinge loss is kind of moving up, moving down, going up, going down. Right? So why do you think this is happening?
I think it's stuck at some local demo.
Okay, that is one way of looking at it. But what is happening here is that the two components of the loss are fighting with each other. Right? So I want to maximize my margin. So I want these bounding planes to expand out. But then whenever I try to move out, my hinge loss is coming in and telling me, no, you can't go. So it's not able to move anywhere.
Like a tug of war game.
Right, yeah, exactly. Right. So this will become even more clear when we go to the case of C equal to 1. C equal to 1 is the interesting part. So let me share that. Okay, is the C equal to 1 case visible to everyone? Yeah. Okay, see what's happening is at epoch 1, you have this kind of a situation. Notice that for all these epochs, the hinge loss is 0 because no points are inside the margin. And my model essentially is happily maximizing the margin. The first part, norm W squared by 2, is going down and down, and my margin is improving. Okay. At epoch 34, you see that the hinge loss becomes non-zero for the first time because of this red color point. Okay, now what do you think will happen?
Modular
Oscillate
decrease.
again.
Sorry, I
It should,
didn't.
it should oscillate again like it was happening in the previous case.
Okay, so it lost like fiercely now, right? So let's see what happens. This is a big jump, right? Why do you think this happened?
Because of the C value that
Exactly.
increased the loss.
Exactly, right? So C value is comparable, right? So C equal to 1 means my hinge loss is comparable to my margin loss, right? So if I move again, if I go forward, the margin will try to increase until it hits another red point. Now it will again change, right? So this will keep happening. See, now it hit
So
a
can you
green.
explain that? Why that change happened? I didn't understand.
Yeah, see, to begin with, you have zero hinge loss. So you are essentially, your objective function looks like minimize norm w square by 2. Okay, so that is your objective function as long as the hinge loss is 0. So minimize norm w square by 2 is the same as maximize the margin. Okay, so I just keep on doing this. My margin is increasing. So all this while the gradient, if you recall, is just w, right? The contribution of the hinge loss either to the loss or to the gradient is 0. So I keep doing this until I hit the red point. When the red point comes inside my margin, I have a non-zero hinge loss. Okay, so now I cannot just maximize my margin alone. I need to make sure that the hinge loss goes down. So because of that, my weights move in such a direction so that the contribution of the hinge loss comes down.
Oh, okay.
Okay, so this will keep happening. So as we go to higher and higher epochs, notice that now it's 80%. Now I drastically change so that it comes down. So right, so this is okay. So one thing I want you all to note is that stopping this at certain number of epochs, right? Because the loss is low, you may not get the correct model. Do you see the point?
Yes, like it is much more better when it was like around 88 or 90.
Right, yeah. So perhaps this is the better model, right? So maybe 94 is very good, but what we ended up with at 100 is probably not the right kind of model. So I would encourage all of you to go back and spend some more time looking at how SVMs work when you do it using gradient descent. I think there is a lot of scope for exploration there.
So I think this is because of the gradient descent. Like we are using gradient descent here. That is why.
Right.
If we use a quadratic programming solver, I think this would be fixed.
This won't happen. Yeah. Okay, so I'll just quickly go back and let's try to do some k-means. Can you give me just 1 or 2 minutes? I'll be back. We'll be back and we'll discuss k-means. Is that okay?
Yes, sir.
Okay. Yeah, sorry. Got delayed. So K-means, do you all know the general procedure for K-means? What should we do?
First we assume three random centroids from the data points. Then we minimize the distance, and along with we change the centroids. I mean, this is what I understand.
Okay. All right. So, what did you cover in Monday's session? Monday's open session. Or any idea what was covered? Anyone who was there for that session? Can you tell me?
It was just a theory part, like we learn about elbow method and everything. Like
Okay. Okay. All right. So, see, in there are like at least two different ways of formulating the loss function, and for I mean what is happening in K-means. So I won't go into all of that. Whatever is required for the collab, that alone we'll do. So I'll just ask a few questions. Okay. Let's say we decide to go with K clusters. So the setting is this: we have n data points and K clusters. Okay, this is the setting. So can someone tell me for each data point xi, we are going to assign one of these K clusters, right? So overall, if you look at the assignment problem, how many assignments are possible? Did you get the question?
Can you repeat, sir?
So we have n data points. So let's say x1, x2, right? So till xn we have, right? So for each data point, I'm going to assign it to some cluster. Let's say I give it C1. Say this belongs to C cluster number 5, right? So on says belongs to cluster number 10, something like that, right? So if you look at this assignments as a vector, right, the vector will be something like C1 comma C5 dot 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 till C10, right? So that is one possible clustering. Now forget about what we are trying to optimize. Overall, how many such cluster assignments are possible? How many such vectors can you come up with?
Vector as in number of vectors in each cluster.
No, not in that way. So see, I'll not do it as variable. We have three clusters, right? And 5 data points. And I say that x3 is in C3, x4 is in C1, xy is in C2. So this is one possible assignment of data points to clusters, right? I count this as one. Now, how many such assignments can you come up with?
So we can have all C1, all C2, all C3. I mean that.
5C3.
Okay, one answer is 5C3. What else? Any other answers? Okay, so think about this way. How many possibilities are there to cluster the first point? I mean, to which cluster can the first point go? How many possibilities are there?
It is 3, sir.
Three, right? Now, for independent of the first data point, for the second data point, how many possibilities are there?
Again, it's 3. I think it will be 3 power 5. Is that
Okay.
the case?
Yeah, you are right.
Oh,
Right? So it
yeah.
is. This is
Because for each of the single data point that we have 3 clusters to choose from, and then it becomes 3 raised to 5. Like
exact,
that.
right. So what you all need to realize is that this is the search space for this algorithm is combinatorial, meaning it will explode as the number of clusters grows or as the number of data points grow. Right? So if you have n data points and k clusters, then you'll have k power n different assignments which are possible. Right? I can cluster them in so many ways. And out of this, I need to pick one such clustering which will optimize my objective. Right? So first thing we need to realize is k-means clustering, getting the exact optimal assignment of clusters is a hard problem, right? It's computationally hard. Okay, so that is one. That's the first thing that I wanted to convey. The second thing is the general algorithm is as follows. So since it is going to be computationally hard, you cannot get hold of the optimal cluster assignment. So you have to settle down for some approximate algorithm, right? So please note that this is k-means is not the best possible clustering. It is an approximate clustering. So the first step is to randomly assign clusters to each of the n data points. That is step one. Step two is until the cluster assignments change, we are going to do this in a loop. Right? What are the things that we are going to do? First thing we are going to do is estimate the cluster centroids. That's step one. Step two, or rather, I'll just call it 2A. Right? 2B is what? Once you estimate the cluster centroids, what do you have to do? Any answers?
Find the distance between the points and the centroid.
Okay, and using those distances, what will you do?
We have to find the centroid which is the minimum distance from all the points. Some of the distance should be minimum.
Okay, so which is the minimum? So which cluster is closest to it, right? So basically, you have to reassign the clusters for all n data points. Right, so step one is like kind of, I won't call this step one, let's call it, this is the initialization. The initialization has again two parts to it. So first part is choose the number of clusters. Right, that is the first step, and then randomly assign clusters to each of the n data points. That is the second step. And the third step in the entire algorithm is keep looping, right? In each iteration of the loop, estimate the centroids of these k clusters and reassign the clusters. Once you estimate that, reassign the clusters for all the n data points, because the cluster centroids would have changed. Therefore, the distance of the points from these new means, new centers would have also changed. Therefore, you have to compute the closest cluster for every data point once again. So that is the next step. So you keep doing this until the point when between one iteration and the next one, the cluster assignments do not change. Okay, so this is the stopping condition. So I would suggest that you go and look up resources for this. There is this result that k means always converges, right? So k means will always converge, and whatever point it converges will be a local optima. It won't be the perfect optimal assignment of clusters to data points, but theory says that k means will always converge. And how do you know when it will converge? When these clusters for each data point, if they do not change from one iteration to the other, then we know that k means has converged.
Excuse me, sir. May I
Yeah.
ask a question?
Yeah, please.
So the fact that it converges to a local optima. So like which local optima is going to converge to is based on the assignment. I mean the initialization of what random clusters we chosen initially, and then it converges to that local optima. Because I mean, like, is there any association between the random initialization and the optima to which it converges?
Yeah, that's a good point. Yes, it depends on your it depends on how you choose. Okay, assuming that k is fixed, it depends on how you choose the initial assignment. So what in practice what is done is you run the k means using different initializations, say 7 times or certain number of times, and you for each of these it will eventually converge. You look at the objective function, value of the objective function.
Right, sir.
Whichever has the smallest loss function, you pick up that model and say that this is the best that I can do. So
understood. Thank you, sir.
So wouldn't all clustering algorithms be always converging to the local optima since there are clusters formed?
There are clusters formed, but they all won't converge to the same cluster.
Yeah, it won't converge, but they wouldn't ever converge to the global optima, right? They would always do to the local optima. There's
a bit, perhaps they might, but for real world data sets, the probability of them converging to the global optima is like negligible.
Okay, sir.
Okay, so we'll go through each of these things step by step. So initially, before we go there, I'll just copy the data set that we have. We are just going to use a similar data set, but we'll use 3 data points instead of 3 clusters instead of 2. So we don't need the y values, right? So this is unsupervised. So y goes out of the picture. It is just x. Okay, and you can't plot the colors. So let me quickly get hold of x1, x2, x3. So mu3, let's say, is at 5, 0, right? So x1, x2, x3. I think this is clear to all of you. I don't need to spend any time on this. Just to be safe, I'll just shuffle my data set, right? I don't want my algorithm to. Okay, so we kind of see 3 clusters here. This is, of course, in the simple case of 2D data, it's clear to us. But for a n-dimensional or n-dimensional data set, this may not be clear at all. So we have the data. Now once we have the data set, let's say k equal to 3, right? So assume that we have chosen k to be 3. Choose the number of clusters. So this is done. Okay, so now randomly assign clusters to each of the n data points. Okay, so how do we do that? Let me call that y. Okay, so let me call that y. Now y is going to be what? Cluster assignments, right? Random cluster assignments. Let us say the clusters are 0, 1, 2, right? So basically 0, 1 all the way till k minus 1. So can someone tell me how do I randomly assign some number of values from this range? How do I do that?
So you will have to calculate Euclidean distance between the point and the cluster center.
Okay, right. So even before that, so what we have to do is we have to assume that to begin with, each point is in some clusters. Okay, so that is a part of the initialization. So what I'm going to do is something like this. Let me know if you all understand. I'm going to sample from the list 0 to k minus 1. I'm going to sample n such points. If you remember, n is the size of the data set. N points are there, right? 25 in this case. Okay, it's not n. It's x dot shape of 0. So here there are 75 points. So please tell me if you all.
So you have to run the k. Yeah.
Yeah.
So would this give always an integer? The choice one?
This will integer as in?
Because our classes are 1, 2, 3, right? So they need, okay.
Okay.
No, yeah. So that I don't know this function choice.
Okay. Yeah. So what this does is choice is sampling with replacement, right? So something, so whatever bin bagging we do, right? Sampling from a data set with replacement. That is what choice does. Choice will sample from this. So I mean, yeah, so there are several things that I kind of truncated into one command. So let us. So what choice does is, if you have a data set like this, it will randomly sample 4 points from this list with uniform. I mean, it assumes uniform distribution across these 3 points.
Okay, sir. Yeah. Thank you, sir.
Okay, so that is what choice does. So what we have done is we have randomly assigned these cluster labels for the n data points that are there in our data set. So that means this is also done. Sorry, this is also done. Okay, so now all that we have to do is run the for loop. So the way I'm going to do that is, there are going to be 2 versions of the cluster. I'm going to call that y previous and y current, right? So what do I mean by that? Y previous is before I update the clusters in step B, and y current is after I update the clusters, right? So once I write this down, it will become clear. Okay, so while not I need to introduce a few things before that. So let's say you have 2 assignments, right? So y1 and y2. So this is say 0, 1, 2, 1, 2, 2, 0, or 1, whatever. And y2 is same in most of the cases, but in some cases it differs, right? So if I want to check if these two assignments are equal, let's say I run y1 double equal to y2. So I'm going to get hold of some booleans, right? So the first assignment matches, second assignment matches, but the third assignments, they don't match, right? The third data point is third cluster here, second cluster here, right? So likewise, fourth data point, they don't match, fifth one matches. Okay, so now if I want to check whether two assignments are matching exactly, there is one function called np.all. So what np.all will do is it will return true if every element of your array is true. Okay, so for example, here every element of the array or list is true. Therefore, np.all will return the value true. Even if a single element is false, the np.all function will return false. Is this clear what np.all does?
Clear, sir.
Okay, so why I'm doing this? I need this because I need to know if two assignments are exactly the same. So what I will do is while np.all, the previous assignment, see if this is true, then that means I need to stop my loop, right? If my previous assignment and current assignment, if they match, then I don't need to run one more iteration of k-means because I have converged. So I need to get out of the loop. So what I'll do is, while this is not true, while the previous and current assignments are different from each other, do steps 3a and 3b. Okay, is the loop condition clear? This is what we need to do. Right, so why previous are two different assignments, right? So is this clear to everyone what the loop condition is saying?
Yes, sir.
Okay.
What is the meaning of convergence here?
Convergence here means, in this context, it means when so how do you, so when you run a loop, right? Let me tell it computationally. So when you run a loop, when it has to terminate at some point, right? So you're asking when will it terminate? Okay, so either you manually terminate it based on some criterion, say after 20 iterations terminate the loop, or maybe it's some other condition, right? If your loss goes below say 0.5, terminate it. Now it turns out that thankfully in the case of k-means, it will certainly terminate after a finite number of iterations, and that is when the cluster assignments do not change from one iteration to the other. So when that happens, we say that the algorithm has converged. Right, so you can think about convergence like what you did in limits, right? Limit 1 n tending to infinity 1 by n. So something similar to that is happening here.
So is there a corner case of infinite loop here?
No, right? So there is, we can actually, this should have been done, but anyway, so we can show that in every iteration, the loss function will keep on decreasing, right? And since there are only k power n possible assignments, right? There are only a finite number of combinations. Even though this might be large, the loop will have to terminate at some point. Okay, so this can actually be proven. So this is a well-established fact that it will always converge, no matter what initial cluster centroids or assignments you choose. It will always converge.
But how it is finding the y current values?
Yeah,
This is initializing, right?
Sorry?
The y previous that you have written, that we are initializing, right?
Yeah, that's a good point. We'll come to that, right? So I'll call this y current, and when the algorithm begins, I'll just assume that y current and y previous are not same. So I'll just randomly set all the values to 0, right? I do this so that my loop, I even enter the loop. Okay, so this is a random set of n values. This is all 0, so they are going to be different. So I'll enter the k-means setup. Okay, now for steps A and B, we need to write function, estimate the cluster centroids. So how do we do that? We need to write two functions. One is to get the centroids, and one is to reassign the points, right? So get assignments. Okay, so what inputs does the function get centroids need?
The data points and the labels.
You need the data points and you need the current assignments, right? So x comma y. Okay, so news, I'm going to call this, there are k centroids, so I'm going to call this news. So it's going to be of size. I also need the number of clusters, right? So I'm going to need the number of clusters k. This is going to be of shape k cross do you all agree with me on this? There are k centroids or k clusters. Each cluster is in the same space as the data points, right? And if the data points are in an m-dimensional space, my cluster centroid will also be in an m-dimensional space. So
yeah, it's like every centroid is like a data point in the m-dimensional space.
M-dimensional space, yeah. So is that okay with others also?
Yes, sir.
Okay, so this is a k cross m array. Now what I'm going to do is I'm going to go through each centroid, or rather each cluster, and I'm going to extract all those points which have label equal to k, and I'm going to get their mean. Okay, now mean will be along which axis? Axis equal to 0 or axis equal to 1?
0.
Axis equal to 0, right? They are all along the rows, we need to get the mean. Now this is news of what? The kth centroid, right? So is that okay? Others, are you all following? Only like
no, sir. This fifth line is not clear.
Okay, so there are if there are 3 clusters, then my news will be like this, right? This is say 1, 2, 3, 4, 5, 6. The first row will correspond to the centroid for cluster 1. Second row will be centroid for cluster 2, and third row for cluster 3. So say for cluster 2, what do? I look at all those data points which have been assigned to cluster 2. That is what this is doing. And I get hold of their mean.
Okay.
And I am assigning that to the second row. So this is nothing but second row, which is kth row. In the kth row, you insert the mean of all those data points which have been assigned to cluster k.
Okay.
Is that okay, or is there still some problem?
No, clear, sir.
Okay, so this is what we are doing, and I think that's all. Right? You can return the centroids. Okay, so this is step 3a, right? You have estimated the cluster centroid. So let's take this. Now what remains is reassign the clusters for all n data points. So you have to get hold of the data points and the current mu's. Using this, you have to reassign the cluster centroids. Rather, sorry, cluster assignments. Okay, so here this is again going to be slightly non-trivial. Let me write concrete values here. 3 clusters are two-dimensional data. So X is of size. X is of size what? Say there are 75 points. So 75, 2. Right? My mu's are of what shape?
3 cross 2.
3 cross 2. 3 mu's, 3 centroids or 3 clusters, each of size 2. So what I need to do is I need to get hold of one data point at a time. Let's call it X of I. This will be the ith row of X, which is one sample. And I'm going to get the Euclidean distance, right? So this is X vector minus mu vector. Sorry, not mu, so I, mu's. And I'm going to square this. And I'm going to add this along axis 1. Now, do you understand what we have done so far? Does this make sense?
I think what we do is we take a single data point.
Mu should be just the mean, right? It is the centroid.
These are the centroids.
So centroids, we are having centroids are the how's it coming in a matrix?
Okay, right. So here again there is broadcasting happening. So see, X is say there are several data points. So I'm just going to use okay, there are 1, 2, 3, 4, 5 cross 2. There are 5 cross 2 data points. So what I'm doing is I am taking something like X of 2, right? I am taking the second data point. Okay, so say X of 1 is the second data point, and I'm doing something like this, right? So sorry. So this is what, by the NumPy broadcasting rules, this is 3, 4 minus this whole thing. Okay, so what you will end up getting is the same matrix, but then 3 minus 1, 4 minus 2, which is 2, 3 minus 3 is 0, 4 minus 4 is 0, 3 minus 5 is minus 2.
But this should be this should be the mean of that particular row, right? The mu's are like 1 and 2 is, well, I'm basically taking the mean of that particular cluster.
This is the cluster mean, right? So I have already obtained my cluster means and I am storing it in mu's.
Okay.
There are 3 clusters. These are the 3 cluster means. One is at 1, 2, one is at 3, 4, one is at 5, 6.
Okay, got it, sir. Right.
Right. So now for each data point, we are doing this. Okay, we are in fact not doing just this. We are raising this to the power 2. Okay, so we are raising this to the power 2. So the whole thing is all element wise, right? So
it's clear, sir. Right.
Right. So this part now I just want to complete what sorry. So this becomes 4, 4, 4, 4, right? Now what we do is we sum along the axis 1. right? So we sum along the axis 1. We end up with
8.
Yeah, so we just delete. Okay, so I hope you all get that part. You just need to okay, so I'm not able to get it, but this is, you understand this, right? 804, that's what we have. Okay.
It will be 808, right?
Yeah, I'm sorry, by mistake I started the recording. Okay, yeah, this will be 808, sorry. Yeah. So what have I computed for each for that particular data point? Can you tell me what I have computed in this process?
The distance, right?
Yeah.
From the centroid. Right?
Yeah, the square distance of this point from each of the centroids. That is what is there in each row. Okay, so let me, for completeness sake, let me write this as 8, 0, 8. Okay, so the first row gives me the distance of x of 1 from mu1. This is distance from mu2. This is distance from mu3.
So this will be aligned to the second centroid, right? This particular point, x1 will be aligned to the second centroid.
X1 will be aligned to the second centroid in the new assignment.
Right.
Okay, so how do we do that? That also will complete. So,
sir, I have a doubt here. So 1 minute.
Yeah.
Sir, you did axis is equal to 1. So which means it does it in the column space, right?
It will do column wise, yeah, across these columns. So axis 0 would mean for 8. Axis equal to 1 means along the column, so it will be 808. So the way to remember this, the way I remember this is axis equal to 0 is down arrow, right? Top to bottom. Axis equal to 1 is, so I remember it this way. So top to bottom, axis equal to 1 is left to right.
Okay.
Okay, so axis equal to 0 would do come from, you will just compress it from top to bottom, and whether it is sum or mean, it will do that from top to bottom. Axis equal to 1 will do from left to right. So whether it is mean or sum, it will compute it along the columns.
Okay, okay. This is different to your np.1s and np. What I mean, all those things, right, sir?
Which one?
No, it's different, sir. Yeah, sorry. Thank you. Yeah.
Right. So yeah. Now the cluster assignment just is argmin of this vector, right? So argmin of this vector will be this cluster. Okay. So we'll just complete that here. So you sum it across axis 1, and you take an argmin. I mean, argmin, there is only one vector, so you don't need to specify axis. So this is the label for the ith data point, and you do this for each of the n data points in your data set, and you finally return that. Okay, so that is the cluster assignment. Is this step clear? Whatever we have done.
So wouldn't we have to append it to a y or something like that?
Oh yeah, sorry. Yeah, y we have to define. Yeah, so np dot zeros of shape x dot 0, x of 0. Right. So we have as many y's as we have data points. Sorry, as many labels as we have data points, and okay, is this clear now? For everyone, I'm assuming it is clear. So we have get centroids, we have get assignments. So let us go back and strike this. So only thing that remains is plugging these things in place. So first step is what? Recomputing, sorry, getting the centroids, right? So get centroids, pass the value of x and the current value of current assignment that you have and the cluster number of clusters, you will get some mu's, right? So based on these mu's, what you have to do is you will have to get the latest assignments. That will give you the new current value.
So in this code, in that line 11, where you put yi, where you're putting that NP, you don't have to append it anywhere.
That I don't need to, because y of I I'm defining.
Okay, right.
Right. So assignments. Right. So this is assignments. Okay. So y current is this. The only thing that is pending is I need to make sure that my y previous gets updated. So if I do just an equal to, they won't end up having the same memory location. So I don't want to do that. So I create a copy of the current labels and I assign it to y previous. Is this clear so far?
Sir, I didn't understand why we are making a copy.
Okay, see, in NumPy, right, you have in NumPy, if you remember Python, you have this problem of, so if you have A and you say B equal to A, and if you change the value of B, right, and if you look at A, what happens to A? A also gets changed. Okay, I mean, this is not a problem here because y current is kind of getting reassigned, but just to be safe, I have made a copy of y current. So if you make a copy of A and then change B, that won't affect A. That's the idea.
Yeah, okay, got it.
Okay, so it's not very essential, but anyway. So let's just run this, and so notice that it converged very quickly. It took only 4 iterations. Okay, so how do we now see if we are doing all this correctly? We just plot it, but this time with the labels. So all this we don't need. We just need to do the scatter plot of x, and if we give c equal to y current, that will give us the labels. I mean the colored plot, right? So these are now with the labels. These are our 3 clusters. Okay, so did you get this part so far?
Yes, sir.
Okay, so there is one interesting thing about k-means. So let's also plot each of these means, right? So this is means of 0, and means of 1. Okay, so should be what scatter.
Excuse me, sir.
Yeah.
That comma is missing in the second argument after the colon.
Oh, okay, nice. Okay.
Yeah.
Okay, so these are the centroids. So now there is, the moment you have these centroids, any new data point, if you want to cluster it, right, a test data point, if you want to cluster it, of course you can find the distances, but there is also something called what is called a Voronoi diagram, right? I don't know if you all have heard of it. Voronoi diagram, right? Let me first show what it is. You can, so
excuse me, sir.
Yeah,
I have a question. May I ask?
Yeah, please go ahead. I'll just keep.
Okay, so the assignment to which cluster? I mean, which data points gets assigned to which cluster is like random, right? Because I was just running the same code, and the colors that I got for each of the different clusters were different. So I was like, I mean, they are not getting assigned to the same cluster.
Yeah. That could
So
change.
the label may vary, is it?
Yeah. Right. So
Okay.
depending on, so in some other assignment, this may become yellow, this may become this aqua color.
So why is it so, sir? I mean, like, what does it
It
depend on?
depends on which initial, how you initialize your centroid. So if you initialize your see, at some point this is deterministic, right? So the moment you initialize your clusters in Y current, right? Random cluster assignments which you do upfront, right? After that, every step is deterministic.
Right, sir.
Right. So it all depends on how you initialize that.
Okay.
Okay. So if you actually plot this, you will get something called a Voronoi diagram, right? So this is called a Voronoi diagram. This part belongs to this cell. So this is, each of these is called a cell, right? So there are 3 cells. So by looking at this image, can someone tell me what this black dotted line represents?
It's like a decision boundary.
Decision boundary, yeah.
Right, it's the decision boundary. So what can you tell me about the distance of points from these two centroids for points which lie on the decision boundary?
So it should be at the middle of the line joining the two centroids.
Yeah, right. So what does it do to the distance? The distance of, so let's say a point is on the decision boundary. What can you tell me about the distance of that point from these two blue points?
Is it equidistant from both the points, sir?
Yeah, exactly. Right. So they have to be equidistant.
Okay. Yeah, right.
Right. So that is the decision boundary. So all points which fall to this side of the boundary will be clustered yellow or will be labeled yellow. Everything to this point will be labeled whatever that color is, right? So this is called a Voronoi diagram, and each of these cells into which it is partitioned, it's called a Voronoi cell. Okay, so this is one point. So I just want to very quickly show you one, since we are already beyond time.
Sir, may I ask one doubt, sir?
Yeah.
So once this, k-means clustering is not an instant-based model, right? I mean, once this training is done, when I put a test data into it, it doesn't recalculate the centroid, right?
No. I mean, assuming you just want to label that, you just want to find what cluster that point belongs to. You don't need to recalibrate the means.
Okay, sir. Yeah, thank you, sir.
Okay, so I just want to show one. I mean, it's the same code that I wrote here. So this is a small demonstration of one application of k-means. I mean, not a very popular application, but if you want to do something like image segmentation, you can take this image, run k-means on it, and this is for k equal to 3, right? So you will end up with 3. So I chose 3 clusters, therefore I got hold of the most important patterns in this particular image. Okay, so it was able to segment this image into some flower plus some background. So this is k equal to 1, let's say. This is cluster 2, and this leaves are cluster 3. If you notice, there are some very blurred leaves visible here. So they belong to cluster 3. Okay, so does anyone want to know how this is done? If you want, we can spend some 5 minutes on this. If not, we can. I mean, that is the end of the session.
Let's
discuss.
Yes, sir.
Sir, there is one another thing, sir. In the lecture video, we saw that Shilotes distance. I don't know if I am pronouncing it right.
That chill out question, right? That part.
Yeah, yes, sir.
Yeah, see, that is given wrongly in the lecture. So don't worry about that question. I mean, That is not part of the syllabus.
Okay.
Okay.
And one graded programming assignment was also given.
Yeah, it is based on that. That is actually wrong. The question's formula is wrong. So, yeah. Anyway, so that is.
So one more doubt in this flower image, the colors are quite distinguishable, right?
Right.
If the colors are matching, and so it won't be able to distinguish properly, or will it distinguish properly?
Yeah, good point. So it won't be. So let's take some other image, and if we can basically run the whole thing.
So can you go through the code for this?
Yeah. So see, first I'll do that. So what's happening here is the SVM code is the same. Sorry, not SVM. The clustering code is the same. But what we are doing here is that we are loading an image. An image is of this size, right? There are 427 cross 640 pixels. There are basically these many pixels in the image, and each pixel comes in three forms, right? It could be either it's an RGB image, so red, green, blue. So if you look at flower of 0, 0, this is the left top pixel in the image, right? 1 second, I need to run the whole thing. Okay, so if you look at the 0, the left top pixel, this is what it is, right? So it will have these three values. So this is the red channel, this is the green channel, and this is the blue channel, right? So each of them will be a value between say 0 and 255. What I've done is I've divided it by the maximum value in the array. So that is why they are fractional values.
Okay.
Okay, so
why have you multiplied the this
yeah. So why I've done that is each pixel I now want each pixel to be one data point for my k-means clustering, right? So therefore, what I have done is I have reshaped this image in this way, so that there are actually these many pixels, 22,73,280 pixels, and each pixel is a three-dimensional vector. So my data matrix of the shape. Okay, so that is what I have done. So I have to now cluster these many points.
Right, sir.
Okay, so the rest of it is same. I choose 3 clusters, the same algorithm. So it converges after 18 iterations. And what I am doing here is that I am choosing the cluster assignments for each of the 2 lakh pixels. Okay, so Y current is the cluster assignment for these 2 lakh pixels, and I am now, instead of using the original pixel values in the image, I am replacing them by the means, one of the 3 means.
So if you change this k to 10, then what will happen?
Okay, then you will get finer detail. So for example, if we do choose k equal to 10, it will take slightly more time because
Sir, one thing, sir, while it is running, in this image, first there were 640 something data points, right?
No, there were
427.
There are actually these many pixels. So 2 lakh pixels are there. 2,73,280 pixels are there.
So 427 is like length. That is the length, no sir?
Yeah, it is one of the 2. So it's either the height in this case.
Okay. The height in this case. Because there is one another like in MLP we use MNIST dataset. They are.
It is 28 by 28, right? So that is
28, yeah.
That is a much smaller. This has too much detail actually. That's why
I think it's taking too much time. Yeah.
Yeah. So
They'll
K
change it to
then
6 or something. Yeah.
yeah. So even I think even 6 might take time. I'll just see if
Yeah. I can experiment.
yeah. Let's just see if there is a simpler data set in sklearn. I don't know how to see the. Okay, there is only China.jpg, flower.jpg. They have nothing else. Okay, maybe let's try it for China. I don't know how it will look. China.jpg. That is also of the same shape, but let's run it with. See, we can run it with any value of k, but smaller value of k is better. Let's just say k equal to 2. Even 2 is taking time.
It is doing 2 to the power 2 lakh. So
Yeah, 12 iterations is what it needed. Okay, I mean that's reasonable. So the background is one color, the foreground is another color. If you look at it, that is the segmentation that we got.
It's fantastic, right?
I mean, sir, these borders and all these like all the borders of the temples or the leaves, they are kind of accurate, sir. Like how this can be this accurate?
It is accurate because in the three-dimensional space, these values are closer to this centroid, right? These borders, see the pixel values on the borders, they all are very close to each other, and therefore they'll be close to that particular centroid, right? So see here, it's the reason we are able to get such a good segmentation is because the original image itself is very well segmented in some sense, right? So there is a very clear background and foreground here. Therefore, segmentation works so well. But
So
yeah,
we can say that the like better the quality of the image, better will be the segmentation.
so less, so better quality, I won't say. I mean, I would call it more decluttered. So if the image is very cluttered, right, with say 100 different objects out there, then my clustering, my segmentation performance will go down because uh, the the difference between two objects, there might be very little difference between them, right? So if, for example, if you have a blue color uh, ball and light blue ball which are next to each other in an image, then maybe I may not be able to get that good of a segmentation, right? Because they are like nearly close to each other.
Yes, sir. Yes, sir.
And another thing, if you just have
So that's
if
why
you
the
take k is equal to 2, then you will probably just get this kind of a black and white kind of an image, right?
Yeah.
Right.
so that's why the sky and the water is not well segmented.
Right, exactly, right. Yeah, that's a good point. Yeah, these are very. So I need k equal to, if we go for k equal to 3, we might get little more detail. I'm not sure, but it'll take again another 2 minutes for that. Anyway, so any other questions?
Based on what exactly it is like dividing color?
RGB, right? So your features are red, green, and blue channels. So yeah, you are right. In some sense, it's based on color is what it's.
But so you have clubbed the colors, right, by multiplying it together.
Multiplying which one you are saying? Multiplying.
So you've multiplied that 427 into 640 together. So which means that color distinguishing RGB is not existing anymore, right?
No, right. See, the RGB part is 3. This dimension. The 427 640 is the spatial extent of the image. It's the number of pixels.
Okay.
Right. So what I'm doing is I'm just in some sense taking each row of this image into, I'm just flattening this image into one long sequence.
Yeah.
Each element in that sequence will have 3 RGB values associated with it.
Okay. Okay.
Okay, so yeah.
Here, sir, you have multiplied this force of 27 into 640. So you have flattened it.
Yeah.
But the output image that doesn't know like what is the length and what is the breadth, like 427 and 640.
That is why I'm reshaping it, right? So that is why I'm reshaping it back.
Okay, thank you.
Okay, so for k equal to 3, we get yeah, I mean, not that good, but perhaps little more detail is there.
Captures the shadows, kind of.
Yeah. Okay, yeah. So that is all we had. Any other questions on SVM on k-means?
So I just had a quick question about k-means. Do we assume something prior, like about k-means, like a distribution or something about the data?
We don't assume any distribution. See, there is one extension to k-means, which is, k-means does a hard kind of clustering, right? There is a hard voting, not voting, a hard labeling in some sense. So either the point belongs to cluster 1 or 2 or 3, but not to, there's no probabilistic thing there, right? So there is an extension to k-means where you can do soft clustering in some sense, where you can assign probabilities to clusters. So you could say, this particular data point, for example, it belongs to cluster yellow with probability 0.75, and it belongs to this with 0.25, something like that you could say. So there you would bring in some distributions to model the whole thing. So those interested, you can read. There is a chapter on k-means in Christopher Bishop's PRML, where they extend k-means to the case of soft clustering, where some probability distributions come in, and it's nicely explained. So you could do that.
And what are the cases in which k-means works best?
For the cases in which it works best, I am not very sure.
It should be separable. I mean, if you have clusters which are separate, then
if there are, yeah, that is one, maybe that could be one thing. And the second is, if your distance metric you are using Euclidean distance metric here, right? So to find the between in cluster distance, right, variation. So that should work, right? So if your features are such that the Euclidean metric is a good one to use, then maybe k-means will do really well, right? And but if your features are such that the Euclidean metric is a bad one to apply, then I think it will be a very bad choice.
So in other words, it will be a min-max, right? You want to maximize the distance between the centroids and then minimize the variance of
each cluster. Yeah. Okay, any other questions?
Excuse me, sir. I have one question.
Yeah.
So in the Voronoi diagram that you have drawn,
yeah.
So what does that orange point, represents?
Orange point would be the point where it's equidistant from all 3 means.
Okay.
Right, because this line is equidistant from these 2. This line is equidistant from these 2. So by extension, if you think about it, this will be the point which is equidistant from. This will be the centroid of, not centroid. If you draw a triangle joining these 3 centroids, right? This will be what for that triangle? I don't know.
It will again be a centroid of the triangle.
Yeah, that's what I was also thinking. But will it be centroid, or what is the point?
Centroid is basically where all the diagonals of the triangle meet.
Okay. Yeah, something like that, I believe, right? So this is going to be the same distance from the centroids. Yeah, that is the orange one. So if some of you remember, this kind of an image also comes up in least squares classification. I don't know how many of you went through that question part tasked in discourse. We had a nice discussion on least square classification. So this kind of an image comes up there also.
So is it the mean of the entire data set? Is it so?
Is it the mean? That's a good question. Okay, if all three bins have equal number of data points, then I think this will be the mean of the entire data set. See, this cluster centroid is what mean of these yellow points, right?
Right, sir.
So this is sigma xi by say n. This is sigma xi by n. So if all these n's are the same, the denominators of these three bins are the same, then it will be sigma xi by n. But you need 3n, right? Yeah, it will be. Okay, no, I don't think so. I don't think it will be the mean of all three. It will be something else.
Okay, so it's just that they are equidistant from all the three means, and that's why the point is there.
That is why the point is there, yeah.
Okay, understood. Thank you so much.
Okay, so is that all? Shall we close then?
So can we calculate the centroids using median also?
No, right? I only using the, I mean, centroid by definition is the mean of these points, right? So median may not be something else.
Okay.
Okay, so yeah, anything else? If not, we can close. Okay, then, yeah, so tomorrow 4 to 6, please remember, those who want to attend this, please to attend this session for bagging and boosting.
4 to 6.
Yeah, I think it's, once again, I'll check the calendar. Oh, I think they haven't sent out the invite yet. Yeah, oh no, it's 6 to 8 is project, 4 to 6, yeah.
Okay, right.
I'll remind them, they need to add the.
Thank you, sir.
Thank you, thank you everyone.
Thank you, sir.
Thank you, sir.
Thank you.